It's me again.
Ready for your PowerPoint?
Sure. Okay, I put that up there because you can't read it. I'm Walter Wynn. I have to clear up something from last week's discussion. Our son Jeffrey was watching by Zoom up in Blacksburg, Virginia. You can't see my shirt. It says New River Computing. That's the company he owns up there, an IT company. And he said I didn't adequately explain negative temperature coefficient of reactivity. So we did send out an email, but real quickly, what happens is in a pressurized water reactor, if you draw more steam out, the steam generator will cool down. If you shut the steam generator will heat up. And the pressurized water, because it is water, as water expands with temperature, the hydrogen atoms are further apart, and the nuclear reduction from high-speed neutrons to thermal neutrons is lower and lower. So it tends to be self-correcting. On the submarine, the reactor plant operator hardly had to move the reactor control rods as we went from slow speed to fast speed and back again. The reactor tends to settle at the temperature it was running, but the rate of the fissions will increase or decrease as required to keep the reactor making the heat. So that probably doesn't clear it up either. And Jeffrey, if you're watching, thank you for correcting it, and happy birthday. Okay, yeah, so Jeffrey's birthday is today. So this is the letter that was written by Leo Szilard and Enrico Fermi for Albert Einstein's signature to say there's a real problem here. The Germans may develop a nuclear bomb. We have to do something about that. We have to get going. And then yeah. Okay. In response, Franklin Roosevelt wrote a letter back to Enrico Fermi saying that basically we're going to look into this. We need to get going. So who put Manhattan in the Manhattan Project? It's not a drink. Okay, this was a very high priority program during the war, or just at the beginning of the war. And it was a crash program. We have to start and we have to go rapidly in every possible way that we can think of. It was a multi-year program because it started in the 40s and it ended up after World War II, which ended in 1945. It was multidisciplined. There were theoretical scientists, there were experimental scientists, there were engineers, mathematicians, explosive experts, anything you can think of, they were part of the Manhattan Project. It was multi-state real estate purchases. They bought hundreds of thousands of acres of land to build things that never existed before and to design equipment that nobody knew whether it would work or not. Multiple facilities were also constructed, and I'll talk about that in a moment. Technical equipment design and construction. The theoreticals would think of something, the engineers would try to figure out how to make something that might do that, and then they all went to work. Management was assigned to the U.S. Corps of Engineers because it was involving many states, many disciplines, much purchasing of real estate and building facilities. And they put it in charge of Colonel Groves. And then as they discussed about it, because he had built the Pentagon on time, on schedule in the early 40s. So they decided, well, if anybody can manage something, he can manage it. And then they said, well, we can't have a colonel interacting with all of these doctors and physicists. So they promoted him to general. So General Groves was in overall charge. The main headquarters was located in the Manhattan District headquarters of the Army Corps of Engineers in New York City. And that's why it became the Manhattan Project. Earlier, not very cleverly, they had set up a uranium committee, and then they thought, well, that's saying too much. We better call it something else. It's the Manhattan Project. So here is where the Manhattan Project was scattered all over Canada and the US. And we'll see the Manhattan Project is over here in New York City. But everywhere you see, these are different aspects of the Manhattan Project where they had bought acreage, built buildings. Oak Ridge was prominent. Some of these other places like Sylacauga, Alabama, was an ordnance works because they needed to do things with ordnance. And Mallinckrodt was a metals company. So you look at all these places and they were all involved somehow in setting up and making the Manhattan Project work. So Alamogordo is where they set off the bomb. Los Alamos is where they designed how to build a bomb and tested things. Richmond Hanford Engineer Works was where they were set up along the Columbia River to make plutonium. Oak Ridge had everything going. They had just about anything you can think of. They decided, we'll start here in Oak Ridge and we'll work around. So that's where they were. This is the Oak Ridge, Tennessee, just a view of it. Oak Ridge, they bought 56,000 acres of land. They built 13,000 buildings, and ultimately 82,000 people lived there in a city that did not exist. Hanford was 40,000 acres, 1,200 buildings, and 51,000 people. And in Los Alamos, they went out. That was actually, they decided to go to Los Alamos because Oppenheimer had a ranch nearby, and he thought that would be a cool place to be. And it was the middle of nothing. So they bought 54,000 acres, and 12,000 people ultimately were at Los Alamos. This is just an idea of the money that was being spent and where it went. So if you look up there, Oak Ridge had the most money, $1.19 billion. And if you convert that to 2020 dollars, it's about 14 billion. So Hanford, where they were making the plutonium, 390 million. Special operating materials is most likely the procurement of uranium from Africa and the development of plutonium and refining it, and the other materials that they needed to build all of the machinery that they were building in all of these other places. Los Alamos, about 75 million. R&D was about 70 million. Government overhead, 37 million, which is not a bad number out of 1.89 billion, and all of the places where they established different offices of the various government activities. And a heavy water plant. They didn't realize at first that they could get a natural uranium reactor up and running so that they could get some plutonium. So they were also involved with the Canadian people who had a lot of access to heavy water. So they built the plants and they brought that down. It was basically, anybody has an idea of how we can do this, how much money do you need? And go spend it and make it work. So let's go way back in history now. I'm going to be showing you some of the people who led us up with their experiments to the point where we actually had uranium fission. So in the Middle Ages, alchemy was the big thing. They were going to convert base metals into gold, and they spent a lot of time trying to do that. It never worked. Then they got into chemistry and they decided that gold is an element. We can't make it from other things. And we can then discover how to make compounds, H2O, CO2. They learned about chemistry and then they decided for sure they were never going to make any gold from base metals. Physics and particle physics was started around the middle of the 1800s with some of the things we'll get into. Radiation in the late 1800s and up through the 1900s, they were discovering radiation, radioactivity, what it can do, what does it mean, where does it come from. The Manhattan Project then is what we're going to really talk about. And then the Manhattan Project, at the end of the war, the civilians were worried about the control of the nuclear materials. So they formed the Atomic Energy Commission for the civilian use of nuclear reactors. And for many years, the fuel in the nuclear reactors being used by power plants was owned by the Atomic Energy Commission. Industrial and medical uses of nuclear radiation, civilian control of nuclear weapons. And after that, they went to the Nuclear Regulatory Commission and the Department of Energy. So let's go, what does it mean? Well, there was no internet in the 1800s, early 1900s, even until just about 20 years ago. So these guys couldn't get together on the internet and chat and get in a chat room and talk about what they were doing. Telephones were either non-existent or very expensive up until, cell phones. So these guys didn't call each other on the telephone. Most of the scientists had attended college. Many of them were self-funded because they were second sons of a lord and they weren't going to inherit the money or the title, but they did have money and they could set up their own labs. They wrote technical letters to journals and they learned about each other's work by reading the letters and the journals. Most of the prestigious journals were in German. That's why John and I and some of the rest of you had to take German as part of our PhD requirement, even though I never read a German article that I needed for any of my work. Just check off one of the boxes. There were very few textbooks written yet, so it was still these journals and personal interactions between the scientists where they were exchanging views. And like I said, some of the early scientists had their own personal labs. Let's see who some of these guys are. This is Julius Plucker. He wanted to see electricity moving. They knew it went through wires because they could light a light bulb or they could make an electromagnet. So something was flowing and he wanted to see it. So he had a partially evacuated discharge tube and he charged one end with plus and one end with minus. And when he turned on the electricity, he could see a green glow in one end, but he never did see the electrons moving back and forth, which is what he wanted to do. Eugene Eugen Goldstein, he discovered the cathode rays. He improved this tube and he could charge it, and the anode is positively charged. It's attracting the electrons. the cathode is negatively charged, it would attract the protons, and it had hydrogen gas in there. So the protons were being pulled through the holes in the cathode. And that was the first time they knew about protons. So he gave the name to the positive ions of protons. The next guy down the street was William Crookes. He improved the vacuum tube, and the little asterisk we'll see as we go along indicate that that person received a Nobel Prize for the work that he did. William Röntgen creates X-rays in a vacuum, and he took a picture of his wife's wedding ring, I believe that was. And so for many years, they were called Röntgen rays, and then they decided X-rays was easier to spell. Okay, now Henri Becquerel discovers uranic rays from uranium. He put a piece of uranium in the drawer with a piece of film, and if you look very carefully, there's a Maltese cross there. So that was between the film and the uranium, and it darkened the film, and so he got credit for discovering uranic rays, got himself a Nobel Prize. Thomson measures electron mass, and that showed that the protons and neutrons are not the smallest form of matter, but electrons were. And if you look at this, if they had done a little bit more with that, this would have turned into a television screen, because the early televisions, you had an electric charge perpendicular to a magnetic force, and you varied the field of the magnetic force and the strength of the electrical force to force the electrons up and down the screen and right and left. Ernest Rutherford discovers alpha and beta particles. He's the first Baron Rutherford from New Zealand. And this is a complicated picture, but basically there's some alpha particles going through a hole in the lead screen with a slit. And there's a gold foil, a very thin gold foil there. And what he was looking by putting detectors around the edge, he was looking to see if the alpha rays penetrated through the gold foil or if they were bounced off the nucleus of the gold atom. And he discovered that they were, and he got himself a Nobel Prize. Pierre and Marie Curie discovered thorium rays and isolated polonium and radium, and the Nobel Prize was going to be offered to Pierre because, of course, he was a man, and he refused to accept the prize unless they also named his wife, Marie, on the Nobel Prize. And she was the first woman to get a Nobel Prize. And so did, she got another one, and so did their daughter. Okay, 1900, Max Planck. He discovered what came to be known as Planck's constant. And what it's telling us is that the energy of a photon is directly proportional to the frequency of the photon. So the energy equals Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength of the particle. And that's a very big, strange number, but that's the way it works. Albert Einstein did not get his Nobel Prize for E equals mc squared, nor for the general theory of relativity. He got it for the photoelectric effect. And we'll talk about that a little bit later. Ernst Rutherford, first Baron Rutherford of Nelson, discovers alpha rays are helium atoms. They knew alpha rays from before because they could bounce them around and they could measure them, but they didn't know exactly what they were. So they started with the first letter in the Greek alphabet, alpha rays, and then they discovered beta rays, which later they figured out were electrons, and gamma rays are radioactive energy from radioactive particles. And then they got to X-rays and Becquerel rays. But in any event, he discovered they are helium atoms. And particle physics history, here Rutherford proposes a solar system model for atoms from alpha scattering experiments. He could see that something was bouncing off a really heavy thing in the middle, and there were electrons, so they must be in the edges somewhere because they're not really interacting with the alpha rays going through. Turns out not to be right. Robert Millikan measures the electron charge to within 1%, and then it's defined as one negative charge. Frederick Soddy proposed atomic weights and isotopes, which ended up as with the periodic table of elements, which we saw last week. Let's see, go back there. So he got the Nobel Prize also. Niels Bohr was a Danish theoretical physicist, and he had proposed the model called the Bohr model for electron structure. And so in the middle, you have the nucleus, and then in the first place for electrons, second place, third place. These are shells, so-called, and he developed the formula for figuring out how many electrons you can put in a shell and it's filled up and can't accept anymore. But this explains the photoelectric effect. So if an electron is excited into a shell with more energy than it would normally be, you have to give it energy to get there. When it falls back to its normal place, it will send off a photon of a particular quantized energy level. Einstein had developed a theory of the photoelectric effect, talking about why it takes a particular frequency of a photon to make an electron be eliminated from an element. Ernest Rutherford bombards nitrogen with alpha and he gets oxygen. And this, you can see an alpha particle 2,4 goes into nitrogen, which is 714, and you get 916, and it throws off a proton, so you end up with 816, which is a standard oxygen. But his research associate or fellow did all the work. He did not get credit. He didn't get the Nobel Prize. And so he has a sad little face there. Now, this is a very interesting guy. Louis Victor Pierre Raymond, 7th Duc de Broglie, frequently was called Prince Louis. But he proposed that the wavelength of photons and particles are the wavelength divided by the 8 equals h, Planck's constant, divided by the momentum of the particle. And he didn't specify that it had to be photons. And we'll see in a little bit that the same equation applies to electrons. Werner von Heisenberg developed a matrix theory of quantum mechanics. Now, matrix algebra is a complex mess, and I never was very good at it. But he got the Nobel Prize for developing a way to calculate where a certain element or proton or electron could be found in a certain experiment. Also, he was the head of the German reactor physics program in World War II. Erwin Schrödinger came up with the wave theory, and the wave theory is a complex, multidimensional differential equation, which when solved, you can determine the probability of finding your elementary particle in a certain place. Much easier to do, at least for me. Then Heisenberg came up with the uncertainty principle. This says that the product of position, like delta x, and the momentum, delta p, has got to be equal to or greater than h bar over 2, Planck's constant. H bar means h divided by pi. So frequently you'll see h bar or just h. He got the Nobel Prize for proposing this uncertainty principle. So you can never know everything about a particle. If you're dealing with electrons, you can know where the particle is, but then you won't know what its energy is. Or you can know its energy, but you won't know where it is. So if you want to try to refine your knowledge about the position of something, it'll never be better refined than h bar over 2. Okay, now we have electron diffraction. And earlier there was a X-ray diffraction, but these are electrons that are going through and they are being scattered at an angle. And it really proved that the electrons can behave as a particle or as a wave. He had another partner who also didn't get named. Here's Paul Dirac. He predicts antimatter looking at the equations with Heisenberg and Schrödinger. He looked at it and he said, well, it doesn't require it to be a positive electron. It could be a negative electron. So he predicts antimatter and got a Nobel Prize. Particle history, Pauli and Fermi predict neutrinos. They were working with equations of radiation, spontaneous radiation, and the electrons being given off. And when they added up all the energy, it didn't add up. So they said there must be another particle that's given off to make the energy come out right. So it must be a very small, small particle with no charge. And so Fermi, being Italian, named it neutrino, which means little neutron. And then Sir James Chadwick, discovers neutrons. And here is Carl Anderson. He discovers positrons in cosmic rays. That is an electron-sized particle that's behaving just like an electron with a negative charge. So Dirac was happy about that. They found them. So here's Frederic Joliot-Curie and Irene Joliot-Curie. They made the first artificially radioactive element, phosphorus-30, for which they both got the Nobel Prize, mother-daughter combination. I mentioned Niels Bohr earlier. His son also has received a Nobel Prize. As far as I know, that's the only two parent-sibling Nobel Prize winners from one family. This is a Japanese physicist, and he proposes the strong force, the strong electromagnetic force. If you look back at Bohr's description of the atom with a big positive charge in the middle, and the electrons are in the outer periphery, so-called rings like a solar system, if those electrons are moving in a circle, they would give off energy and fall into the middle. But you have in the middle, you have a whole bunch of positive charges being held together with some neutrons. And we all know that positive or like charges repel and unlike charges attract. So he proposes the strong electromagnetic force that only acts inside the nucleus, and it allows the positive protons to be held together and not blow themselves apart from the middle of the atom. Hans Bethe proposes fusion for sun power. Now, I had Hans Bethe for a quantum mechanics course at Cornell. He did not receive the Nobel Prize until after I was in his course. So is that coincidence? Or did I have some influence over him? Certainly not. Enrico Fermi was experimenting with slow neutrons in 1935 or 6. And he thought he was creating transuranic elements because he was bombarding uranium with neutrons and finding something different from the uranium there. So he actually discovered fusion, but he didn't know it. But he got his Nobel Prize for his work with slow neutrons and the difference that they made in nuclear reactions. Otto Hahn and Lisa Meitner bombard uranium with neutrons and discover fission. Szilard proposes a chain reaction or a nuclear bomb. And he wrote the famous letter that Einstein signed, which ended up creating the Manhattan Project. So these are the guys that came before everything that caused the Manhattan Project to be initiated. Macmillan and Seaborg bombard uranium, create the first transuranic elements, and then Seaborg became the head of the Manhattan Project in the Chicago area. He was a chemist, and his problem to solve was how can you separate plutonium from uranium? And it's a different chemical, so a chemical reaction can be used to separate. And then the famous P1 or pile number 1, the graphite blocks pile containing sintered natural uranium. And some 40,000 of these blocks were made, and they had to be ultra pure graphite because impurities in graphite absorb the neutrons, and they figured that out. And it was a huge order of graphite to put this pile together. And you can see from the bottom that they were piling them up in a cube. And when he got up to about the 2/3 point, he realized that he didn't need the complete cube because the neutrons, if there were any from fission, were not escaping out that much of the graphite, and they kept piling them on until one day he worked his slide rule around and said, the number of fissions are increasing exponentially. We have a reactor that's actually working. So in 39, Fermi came to the US in 38. He went to accept his Nobel Prize, taking the train through Germany with his Jewish wife, who had converted to Catholicism the day before, so her passport would not say Jew. And they went through Nazi Germany up to Stockholm, and he never came back. But anyway, in 39, Fermi met with the Navy from the Navy Research Lab in DC suburbs, and they talked about nuclear energy, and some of the guys in the Naval Research Lab got very interested in the possibility of nuclear power for ships. Einstein agrees to meet with FDR, which he did in 1939. World War II begins with the invasion of Poland, September the 1st, 1939. November 39, the Advisory Committee on Uranium was formed, and then they discovered this is a bad name for trying to do a secret project with uranium. In 1940, $6,000 was given to the Advisory Committee on Uranium to research fission. 1940, U-235 is confirmed to be the one responsible for fission. In the summer of 40, Cal Berkeley discovers neptunium, which was one of the transuranic elements, and then they discovered plutonium shortly thereafter. In May of 41, there was a report given to the president and to the bigwigs saying the bomb will not be available before 1945. Chain reaction in natural uranium is 18 months off. An additional year to create enough plutonium. 3 to 5 years to separate enough U-235 to make a bomb. And then they had to go into the isotope separation, centrifuges, electromagnetic separation, gaseous diffusion, thermal diffusion, and then last week I said something about laser diffusion, which I didn't know anything about. And we don't need to know either. December 7, 41, Pearl Harbor. December 6, 42, project headed by Vannevar Bush. May of 42, start all the processes to get U-235. Like I said, if anybody has an idea, you get money, you go and work on it. So June 42, Army Corps of Engineers is now leading it. For the reasons I mentioned, Manhattan Engineer District is leading the whole thing. There's General Groves. He's now a 3-star general. He started out leading the project as a colonel. Okay, in the fall of 42, sites are selected and under contract. Oak Ridge, Tennessee, Los Alamos, New Mexico, Hanford, Washington for plutonium production. And plutonium is chemically different from uranium, and it can be separated from spent fuel chemically, but not easily. So this is just showing on the lower right the process. Neutron capture in U-238 makes U-239, gives off a beta particle in a 23-minute half-life, and it becomes neptunium-239. It gives off another beta particle, half-life of 2.3 days, I think. Yeah, Europeans use 2,3 to mean 2.3, and that turns into plutonium-239. And it is also fissionable. Fall of 42, the sites are selected under contract. What'd I do, go backwards? Los Alamos is the bomb design team. Hanford is plutonium production. 42, Fermi first controlled chain reaction in the Chicago pile. Oppenheimer is sent to Los Angeles in spite of the fact that he was a communist and well known to have been a communist, but they figured he's the guy that can crack the whip on the rest of these scientists and get them moving the way we need them to get them moving. The Manhattan Project in 44 was spending more than $1 billion a year. May of 745, Germany surrenders, and that's really critically important. It's just good fortune for the world that they surrendered before we had a nuclear weapon and dropped it somewhere in Europe. That would have been like the old chief bosun mate teaching me to tie knots would say, that would be a catastrophe. Summer of 45, they have enough 239 plutonium to build a bomb. July 16th of 1945, the Trinity test plutonium bomb first airburst, And they used the plutonium because by now they had more plutonium than they did U-235. So the first bomb, nobody knew it was going to work. They put it on a steel tower, which no longer exists. When it went off, it melted everything. And people were standing back a few miles waiting to look to see what would happen. Some people were positing that the nuclear bomb would be set off and the atmosphere would go ablaze and the world would be over. Fortunately, that didn't happen. This is the Trinity test in Los Alamos of the first nuclear weapon on Earth. The Manhattan Project Timeline 4, August 6th, the untested U-235 bomb was dropped on Hiroshima, or Hiroshima, whatever way is correct to pronounce it. Plutonium-239 bomb, the Fat Man, was dropped over Nagasaki. In August 14, Japan surrenders. This is a picture on the battleship Missouri with the Japanese delegation in formal dress came aboard. General MacArthur is sitting here as the U.S. representative to sign the peace pact. Next week, nuclear power program, Admiral Hyman George Rickover, also known frequently as the kindly old gentleman, and there are other terms that people used about him, and you'll see why next week. But basically, he started it, he ran it, and it worked. Okay. Oh, look, very few people are asleep. This is amazing. I told you to bring your pillows.
Thank you, Walter. All right, so I'm looking for some hands for questions from our Oak Room or online here. Speechless. You left us speechless. Questions or comments?
Questions, comments? Anything online?
No. How
Oh,
about
wait, here we go. I saw Will's hand first.
I was going to ask if the birthday boy had any questions online.
I think, Walter, one of the interesting things was the location of Oak Ridge was because of TVA and the availability of power. The location of Hanford would be because of the Columbia River and the dams and the location of power. So
That's correct.
a lot of electrical.
And once again, I neglected to mention something important. John, you had your hand up.
Yeah, just kind of a side note. When I was a graduate student at Berkeley, I was surrounded by people who worked on the Manhattan Project. At Berkeley, I was a chemistry major, and after 2 years of courses, you had to pick a thesis advisor. And the first person that I interviewed, who interviewed me, was Glenn Seaborn, who had just won a Nobel Prize. And he said that he was not taking any more graduate students because he was getting ready to become chancellor of the University of California at Berkeley. But he recommended that I go with the person that he worked most closely with in Chicago. His name was Burris Cunningham. And so I went to work for Burris Cunningham. Burris Cunningham was a microchemist whose job it was to separate the first few micrograms of plutonium and learn enough about their chemistry that they could begin to make a bomb from plutonium. He was a wonderful, ingenious man. My first job with him was to take a wastebasket full of several kilograms of plutonium and extract from them a tiny bit of curium. And I worked in a glove box with a plastic wastebasket full of plutonium.
And you're still here.
And I'm still here. I was careful. I was carefully supervised. Thank God. But I was never comfortable with working with large amounts of nuclear material. So I proposed another thesis material. But I was just amazed at the ability of Burris Cunningham to work with exceedingly tiny amounts of material. But after doing plutonium, why then he moved up to determining the chemical properties of curium and then the heavier actinides. But he was a wonderful man, but he also got a lot of nuclear exposure, and he died at age 60.
Mm-hmm.
All right, Walter, I do have a question here. Oh, I'm sorry. Did you want to make any comments about that?
Yeah, I was going to just comment that while I was at Cornell, one of my professors for classical mechanics and physics department was Philip Morrison, who went on to run a TV series, but he talked about being at Los Alamos and working with people that were working with plutonium. And there was one man who got a little too much plutonium on his work table, and it started to go, and he knocked it over with his arm, but he died pretty soon after of severe radiation exposure. Wow. They did not know how much it was going to take. And when we talk about the nuclear disasters, there's a place in Russia that we'll talk about where they've had a number of accidental supercritical reactions with people dead and explosions and so forth.
Thank you. Bud Shorstein, go ahead.
It was said that the secrecy of the Manhattan Project was so large that even Harry Truman, as vice president, did not know of the project until after Roosevelt died. And my question is, and I had worked 12 years in the United States Senate, how in the world did they keep the expenditure secret so that no one knew of the project was going on? $1 billion was a lot of money to be spending in the early 1940s.
Yeah, it certainly was, but I know from my own personal experience with different secret projects that they're able to hide big piles of money and call it something like algal research, or give it a strange name that nobody will really care about, and then they can put that money together. We did a project when I was at System Planning Corporation measuring radar cross-section of Army helicopters, and this Army colonel came and said, well, how do you guys want to be paid? I have a suitcase full of money. I said, no, go away. We'll send you an invoice and you send a check from whatever place you send checks. But they can hide a lot of money. But it was secret, and Harry Truman knew nothing about it until a few days after he was installed as President of the United States on FDR's death.
Thank you. Any other questions?
One in the back.
Just a comment that, interestingly enough, the Manhattan Project was not the most expensive project of World War II. Actually, the most expensive project was the development of the B-29 bomber, which was instrumental, basically, in destroying Japan and its war machine. But yeah.
Thank you, Elliot. I didn't know that. Any other questions here in the Oak Room? Seeing none?
Well, we thank you again, Walter, and we look forward to the third session next week. Any preview on what our topic will be?
Yarvar, you're absolutely right, Vice Admiral Rickover.
Yep.
That was the appropriate thing that we never said to him, but it was one of the things we said, among other things. about the kindly old gentleman. So we'll talk about the nuclear navy, its establishment, and how far it's gone and what it's doing today.
All right, thank you. Join us next week.